You think light moves, don't you? I mean, of course it does. Flip a switch. A photon, a little bullet of light, zooms from the bulb to your eye at 300 million meters per second. A wave ripples out from a star, crossing the empty void of space to reach us. It travels. It moves. Simple. But here's the problem. That picture, the little bullet, the elegant wave, is a complete and utter lie. A comforting story we tell ourselves. It's wrong in a way so fundamental it unravels our very idea of what moving even means. What if I told you that light doesn't actually go from here to there? That a photon isn't a thing that travels? That the speed of light, this cosmic speed limit, isn't about something moving at all, but about something else entirely, a fundamental stiffness in the fabric of reality itself? What is light actually doing? Let me show you what I mean. We are all prisoners of our intuition, shaped by a world of baseballs and sound waves and water ripples. So when we imagine light, we force it into one of these two comfortable boxes. First, the particle. Newton loved this idea. A little corpuscle. You shoot it from a source. It flies in a straight line, bink, hits your retina. It has a position, a speed, a trajectory. It moves. This explains shadows, laser pointers, the photoelectric effect. Clean. Second, the wave. Young, Frizzell, Maxwell, they gave us this beautiful undulating creature. An electric field wiggles here. A magnetic field wiggles perpendicular to it, and this self-sustaining disturbance propagates through space, like a wave in a pond. This explains interference, diffraction, color, elegant. And for centuries, physicists fought. Is it a particle or a wave? The answer, as you might have heard, is a frustrating both, or neither. But we usually leave it there, with this mysterious quantum duality. A particle that sometimes acts like a wave that sometimes acts like a particle. But I want to push further, because both ideas, the bullet and the ripple, share one deep, hidden assumption. They assume that something is traveling. Some entity is making a journey from point A to point B. Whether it's a localized bullet or a spread-out wavefront, we picture a thing in motion. This assumption is so natural, so baked into our language. Light travels, it races, it zooms, that we never stop to question it. We've measured its speed with incredible precision, 299,790,458 meters per second. Not a shred of doubt. Case closed. But what if we're measuring the wrong thing? What if that number isn't the speed of an object, but something far stranger? The stage is set by a simple, almost childish question. When you turn on a lamp, what, exactly, is it that leaves the filament and arrives at the wall? The classical answers are comforting. They are also completely inadequate. To see why, we have to go back to where our modern confusion began, not with a grand theory, but with a few stubborn numbers that refuse to fit. Our story doesn't start with relativity or quantum mechanics. It starts in a laboratory in the late 19th century with a man named Albert Michelson. He was obsessed with light and with measuring its speed more precisely than anyone had before. But more than that, he was trying to measure the speed of the Earth itself through the mysterious invisible substance everyone believed light had to travel through, the luminiferous ether. Think of the ether like an invisible stationary ocean filling all of space. Just as sound waves are vibrations in air, light waves, it was thought, were vibrations in this ether. So if the Earth is moving through this ether as it orbits the sun, there should be an aether wind blowing past us. And just as you swim faster downstream than upstream, a beam of light traveling with this wind should go slightly faster than a beam traveling against it. Michelson, with his colleague Richard Morley, built an exquisitely sensitive device called an interferometer. The idea was beautiful in its simplicity. Split a beam of light, send the two halves on perpendicular journeys of exactly equal length, bounce them back and reunite them. If one beam was aided or hindered by the ether wind, the two waves would get out of sync. They would interfere, creating a telltale pattern of light and dark fringes. By rotating the apparatus, they could measure the direction and speed of the ether wind. They prepared for a small but measurable shift in the interference pattern. They calculated. They checked their mirrors. They waited for the fringes to dance. Nothing happened. The fringes remained rock steady. No shift. No wind. It was as if the Earth were standing still in the ether, an impossible result. They repeated the experiment at different times of the year. Nothing. The most famous failed experiment in history. This was huge. The ether, this cornerstone of physics for centuries, simply wasn't there. Or if it was, it had a property nobody had imagined. It dragged along perfectly with the Earth, which was absurd. The stage was set for a revolution. Enter a young patent clerk and burn. Albert Einstein looked at Michelson and Morley's null result and asked a terrifyingly simple question. What if we just accept it? What if the speed of light is always the same? 299, 790 458 meters per second, no matter how fast you are moving. Think about what that means for a second. If you're in a spaceship chasing a beam of light and you measure its speed, you'd expect to see it crawling away from you slowly. But Einstein said, no. You will measure it moving away from you at exactly the same speed as if you were standing still. It defies all common sense about adding velocities. It shreds our idea of a universal clock. This single postulate, the constancy of the speed of light, led him to special relativity. Time dilates, length contracts, mass and energy become equivalent. But even here, in this breathtaking new theory, light is still something that propagates, a signal, a wavefront. Einstein had banished the ether, but the motion of light remained central. Now, let's jump to another thread. The early 1900s. Physicists were staring at another mystery, the photoelectric effect. Shine light on a metal, and it kicks out electrons. The classical wave theory said, make the light brighter, more intense. The electrons should come flying out with more energy, but that's not what happened. Instead, the color of the light determined the electron's energy. Blue light kicked out high-energy electrons, even if it was dim. Red light, no matter how blindingly bright, wouldn't eject electrons at all. In 1905, the same year as his relativity paper, Einstein offered another radical solution. Maybe light isn't just a continuous wave. Maybe it comes in little packets quanta, later called photons. Each packet has an energy tied directly to its color, its frequency. To explain the photoelectric effect, you had to think of light as a stream of these particle-like packets. For this he won the Nobel Prize. So now we have a real mess. On one hand, Michelson Morley and Relativity demand we treat light as a wave without a medium with a fixed speed. On the other, the photoelectric effect demands we treat it as particles. Which is it? The next decade saw the birth of quantum mechanics, a framework so bizarre it made relativity look tame. People like Heisenberg, Schrödinger, and Dirac developed the mathematics. Light and all particles were described by probability waves. A photon isn't here or there until you measure it. It's smeared out in a cloud of possibility. Its path isn't a line, but a sum of all possible paths. And this is where I entered the story. In the 1940s, I was working on a new way to understand quantum mechanics, especially quantum electrodynamics, the theory of how light and electrons interact. I got frustrated with the abstract, ghostly wave functions. I wanted a picture, a way to calculate what happens that felt more concrete, even if the answer was insane. So I developed the path integral formulation. Forget a single path. If a photon goes from a light bulb to your eye, it doesn't take one straight route. It takes every possible route at once. It goes in a dead straight line. It also goes in a wild loop-de-loop around the moon and back. It goes to the Andromeda Galaxy and makes a U-turn. Every single imaginable path is taken. Each path has a certain amplitude, a complex number related to its probability, and you sum or integrate over all these paths to find out where the photon is likely to be detected. This sounds like nonsense, but the mathematics is precise, and it predicts the outcomes of experiments with staggering accuracy to more than 10 decimal places, the most precise predictions in all of science. So let's pause, look at the historical arc, from the solid mechanical aether to its shocking absence, to light as a wave of constant speed, to light as a particle, to light as a probability cloud, to light as a sum over all histories. With each step, the simple idea of a thing moving through space became fuzzier, more abstract, less tenable. We weren't just refining an idea, we were dismantling it. We were preparing to ask, if light isn't following a path, then in what sense is it moving at all? All right, so we've set the stage. We've banished the aether, embraced the constant speed of light, and accepted the weird quantum duality. Now, I want to pull back the curtain on what's really happening, and to do that, we need to talk about fields. Forget particles for a minute. Forget little balls. Think of the universe not as a collection of things, but as a stage. And the stage isn't empty, it's filled with fields, invisible, intangible entities that exist at every single point in space. A temperature field tells you how hot it is at every location. The gravitational field tells you how strongly gravity pulls at every point. And the electromagnetic field, this is the star of our show, tells you the electric and magnetic forces that would act on a charge at any given spot. Now, here's the key. These fields aren't just mathematical bookkeeping. They are the fundamental reality. What we call an electron is not a tiny hard sphere. It is a localized excitation, a little knot of energy in the electron field. A photon is an excitation, a little bundle of energy in the electromagnetic field. Let me say that again because it's crucial. A photon is the electromagnetic field, or more precisely, it is a quantum of vibration of the field. Or more precisely, it is a quantum of vibration of the field. It is not a separate thing that travels through the field like a fish through water. It is the water itself, wiggling in a specific, quantized way. This changes everything. Imagine you have a perfectly still pond. This is the electromagnetic field in its ground state, quiet, dormant. Now, you drop a pebble. A ripple spreads out. In the classical view, that ripple is a thing that moves from the center outward. But in the field view, you didn't add a ripple object to the pond. You added energy at one point. That energy caused the water's surface, the field at that point, to displace. That displacement then couples to the neighboring points, causing them to displace, and so on. What moves is the pattern of excitation, the influence, not a substance. Now let's make this quantum. In our quantum field pond, you can't just create any size ripple. You can only create ripples in discrete minimum energy units. 1 unit is 1 photon. 2 units is 2 photons. You can't have half a photon. So, you have an electron in an atom that gets excited. That's energy added to the electron field. When it falls back down, that energy doesn't just vanish. Conservation of energy is the strictest sheriff in the universe. That energy has to go somewhere. It is donated to the electromagnetic field. But the field can only accept energy in these discrete packets. So, at the location of the electromagnetic field accepts 1 packet of energy. 1 photon is created. But what does created mean? It means the field at that point is now in a higher energy, excited state. And here's where it gets strange. This excitation isn't stable. The field wants to be in its lowest energy state. So this knot of energy, this excitation, doesn't sit still. The rules of quantum mechanics and special relativity woven together into quantum field theory dictate how this excitation propagates. And the rule is, it propagates at exactly 299,792,72458 Mayan 797,92458 Miles Lush. Not because something is moving at that speed, but because that is the fundamental coupling speed of the field. It is the maximum rate at which a disturbance at point A can influence point B. It's not a speed limit for objects. It's a speed limit for cause and effect, for information. Let's do a thought experiment. Think of the field as an infinite grid of matrices, all tightly connected by springs. Push down on one mattress, create an excitation. The springs compress and transfer that push to the neighboring mattresses, which push on their neighbors, and so on. A wave of compression spreads out. The disturbance moves, but no mattress actually travels from the center to the edge. Each mattress just moves up and down locally. What travels is the state of being compressed. This is closer to what a photon is. Now here's my path integral picture, which makes this even clearer and even weirder. Let's ask, how does the field at point B, say your retina, know that the field at point A, a light bulb, got excited? The classical answer, a photon traveled the straight line path between them. My answer, the field at B samples or feels the influence from the field at A via every single possible path connecting them. Think of it like this. You're in New York, and I'm in Los Angeles. I want to send you a message. In the old view, I write a letter, the photon, and put it on a direct flight, the straight path. In the quantum field view, I write an infinite number of identical letters. I put one on every possible route between us. The direct flight, a flight via Tokyo, a flight via London, a bus, a car, a bicycle, a rocket that goes to Mars and back, a path that zigzags crazily across the continent. Every single letter has a little phase tag on it, like a complex number clock hand that spins depending on the path length. When you in LA collect all these letters, you don't just read one. You have to superimpose them all, adding up their clock hands. For almost all of the insane, loopy paths, the clock hands are all pointing in random directions. They cancel each other out. 0. But for the paths very, very close to the straight line path, the clock hands are nearly in sync. They reinforce each other. They add up to a strong signal. So, the influence that reaches you, the detection of a photon, is the result of a constructive interference of an infinity of possibilities. The photon didn't take all those paths. The field interaction is computed over all those paths. The photon is just the name we give to the fact that when the math is done, the energy arrived in one discrete lump at B. This is why I sometimes say a photon doesn't have a path until you measure it. It's not that it has a secret path. The concept of a classical trajectory does not apply. We are seeing the propagation of a correlation in the field. And this leads us to the deepest, most counterintuitive part, virtual particles. In the tiny gaps between the mattress springs, in the quantum froth of empty space, the field is never perfectly still. The Heisenberg uncertainty principle allows for fleeting violations of energy conservation. So, at every point, particle-antiparticle pairs like electrons and positrons are constantly popping into and out of existence. They are virtual. When our real photon, our excitation, propagates, it doesn't just sail through empty space. It interacts with a sea of virtual particles. It can momentarily split into a virtual electron-positron pair, which then recombine. It gets absorbed and re-emitted. Its path is a chaotic dance of interactions with the underlying quantum foam of all fields. So, what are we measuring when we measure the speed of light? We are measuring the effective propagation speed of a disturbance through this interacting quantum field medium. The number c is a fundamental property of space-time itself, woven into the geometry of the universe by relativity, and manifested as the characteristic coupling constant of the electromagnetic field in quantum field theory. Let's put numbers to this weirdness. The time it takes light to cross a proton, about 10 hump-pump-fine meters, is roughly 3 × 10⁻² squared seconds. In that unimaginably brief instant, according to quantum field theory, the propagating excitation that will become our detected photon has sampled an astronomically large number of virtual particle interactions. Its journey is not a clean voyage. It's a staggeringly complex statistical process. Common sense objects, but wait! I can point a laser at the moon and see the dot. Something clearly traveled in a straight line. And you're right, the classical approximation is excellent. The sum over all paths overwhelmingly favors the straight line, classical trajectory. The weird quantum paths cancel out over long distances. But if you set up an experiment sensitive enough like a double-slit experiment with single photons, you see the ghostly influence of all paths. The photon doesn't go through one slit or the other. The field's influence goes through both, interferes, and dictates where the excitation will manifest as a click on your detector. So, is light moving? In the sense of a little bullet traversing space, no. Absolutely not. That picture is dead. What is happening is this. The universe is a dynamic tapestry of quantum fields. An event at one point, an electron dropping energy levels, creates a localized excitation in the electromagnetic field component of that tapestry. The laws of physics, relativity, and quantum mechanics combined dictates how that excitation correlates with other points in the field. The correlation pattern propagates outward at the speed c. When this correlation interacts with another part of the field tied to matter, like an electron in your detector, it can cause a localized transfer of energy, a click. We call that transfer the arrival of a photon. The speed of light is the speed of this correlation. It is the cosmic speed limit for influence, for causality. You see, we've been mistaking the map for the territory. We see a spot of light move across a wall, and our brain, honed by evolution, screams, "Object in motion." Physics is telling us to quiet that instinct. There is no object. There is only the field, vibrating, correlating, and occasionally manifesting a piece of measurable reality in a way that our classical minds interpret as movement. So, let's bring this all together. Why is light not actually moving? Because we have to unlearn what moving means. In our everyday world, moving implies an object, a thing with a persistent identity changing its location against a background of space. A baseball flies from the pitcher's hand to the catcher's mitt. The same atoms, the same leather go on a journey. Light was never that. We just tried to force it into that box. First, we tried the particle box, a little bullet, shattered by interference and the wave nature of light. Then we tried the wave box, a ripple in a medium, shattered by the photoelectric effect and the death of the ether. Quantum mechanics said it's both, a probabilistic wavicle. But we still smuggled in the idea that traveling along some fuzzy path, quantum field theory, the path integral, pulls the final rug out. The fundamental entities, the field, everywhere. A photon is not an object in the field. It is a state of the field. A specific, quantized configuration of energy. Think of it like this. Imagine a vast, silent forest at night. This is the electromagnetic field at rest. Now, in one tree, a cricket chirps. That's the creation of a photon. The sound spreads through the forest. But does the chirp move? No. The air molecules each vibrate locally, passing the vibrational energy along. What propagates is the pattern of compression, the information that a chirp happened. The cricket's chirp doesn't exist in one place and then another. The forest in its entirety takes on the property of containing a chirp and a spreading pattern. Our photon is that chirp in the forest of the electromagnetic field. The speed of light is the speed of sound in that particular forest, a property of the forest itself, not of the chirp. The path integral gives the staggering mechanism. Every possible path for that influence is considered. The straight line is just the path of constructive interference, where the infinite number of quantum clocks tick in sync. The photon we detect is the result of that universe-wide calculation, not the completion of a journey. So, when you look at a star, you are not receiving a tiny traveler that has braved the interstellar void for years. You are feeling a distant tremor in the fabric of reality. The star, years ago, excited the field at its location. That excitation set off a chain of correlations, a cascade of cause and effect through the quantum field that fills what we call space. That correlation propagated outward at the speed c. It interacted with the virtual particle form. It sampled all of space-time, and finally it coupled to the electrons in your telescope or your eye, depositing its energy. The light from the star didn't come to you. The field here and the field there became correlated in a specific way because of an event years ago. You are not seeing the past. You are connected to the past through the immutable rigid geometry of space-time and quantum fields. The number 299,792,458 Meanian 6 secs is not a speed record. It is the conversion factor between space and time in the universe's geometry. It is the coupling constant of the electromagnetic interaction. It is the ultimate rate of information processing in the cosmic quantum computer. We asked, what is moving? The answer, nothing is moving in the classical sense. Instead, reality is computing, and the phenomenon we call light is one of the most beautiful and profound readouts of that computation. This is the thing about physics. It doesn't care what feels natural. It doesn't care about our stories of little balls and ripples. It relentlessly shows us that reality, when you look closely enough, operates on principles far stranger and more magnificent than our intuition could ever invent. We cling to the idea of motion because it's the narrative of our lives. But the universe isn't telling a story of things moving through space. It's revealing a dynamic, interconnected computation, a constant, silent hum of fields exchanging energy and information, bound by the strict, elegant rules of quantum probability and relativistic geometry. Understanding light isn't about visualizing a traveler. It's about accepting a connection, a correlation, a truth that is everywhere at once, yet only manifests here and there, in clicks and flashes, when the cosmic calculation demands it. That's the beauty of physics. Not comfort, not simplicity. Truth. And the truth is, we are not separate observers watching a show of moving lights. We are participants in a field, feeling its vibrations, connected to the farthest star by the silent, instantaneous threads of quantum possibility, propagating at the only speed the universe allows, the speed of cause itself.